So prior to the break, we looked at Cartesian geometry, so where we do things on the number plane. Now we're going to look at Euclidean geometry, named after Euclid, famous Greek mathematician. But they are interchangeable, of course. Remember, Euclid, just as when we saw in coordinate geometry, we sometimes use some of these geometry ideas to solve problems. It is actually possible to go the other way as well. You could solve geometry problems using coordinate geometry ideas. A lot rarer that way, but it is possible. It's all geometry. It's all geometry. But to start with, let's have a look at some notations and things like that we use in geometry in different definitions. So here we go. We'll remember two vertical lines is parallel to, the upside down T is perpendicular to, three horizontal lines is congruent, three vertical lines is similar. The triangle of dots in that configuration, therefore, the other way round, it's not used that often, but that is a notation for because. Some people, when you're writing a reason, sometimes people like to say, oh, because of this. And so they'll put three dots in the upside down triangle. It's probably not used that often these days, but if you ever do see the upside down triangle, that means because. This is why it can happen. So terminologies, produced. So when we see the word produced in geometry, it basically means we're extending a line to a certain point. And the way we say it's important. So here's a line, or probably more correct to say an interval, xy. If I was going to say xy is produced to A, then that's the order I go. xy produce to A. Okay? So the way it's written is telling you how you would redraw the line. As opposed if I wanted it on the other side, then I'd say, oh, well, yx is produced to B. Okay? Foot is often a word we use in geometry to mean the base or the bottom, the foot of the perpendicular, things like that. Doesn't necessarily actually have to be at the bottom. B is still called the foot of the perpendicular in that situation. Collinear, well, we talked about that in coordinate geometry as well. So points that lie on the same line, and concurrent lines that go through the same point. A transversal. A transversal is any line that cuts two or more other lines. And we most commonly see that in our parallel line problems, where you see a line coming through and cutting a couple of parallel lines. That's called a transversal. So conventions is how we name things. And the reason it's important we all do it the same way is because remember, you're writing a proof and someone needs to read your solution and understand what you're talking about. And so if you're naming an angle or a triangle, and they might want to reproduce the diagram, it's important that you let them know how the letters are arranged or which vertex is which and so on. So any angle or polygon we always name in cyclic order, so as we go around the shape. Now, it doesn't matter whether you go clockwise or anti-clockwise, that's fine, but you just go around in order, and that's how you name the shape. So this angle, I could call angle ABC with an angle symbol out the front. Sometimes, instead of putting the angle symbol at the front, we put a little, what do they call those? Is it a caret? Yeah, anyway, that symbol, we put it above the actual vertex. So that also means angle ABC. If there was no ambiguity, then sometimes we just name the vertex and we call it angle B. And what I mean by no ambiguity is it's clear which angle I'm talking about. I mean, if I had vertically opposite angles and said, I'm talking about the angle C, well, that's ambiguous. There's four different angles I could be talking about. So I wouldn't use that notation in that situation. I would name it ACB or ECA, depending on which one I'm talking about. But if there's no mistake about which angle, then you can just use the vertex. You might be thinking, oh, but hang on a sec. Are you talking about the acute angle or are you talking about the reflex angle? And we always assume we're talking about the smaller angle unless mentioned otherwise. So if I was talking about the large angle, I would call it reflex angle, ABC, to highlight I'm talking about the larger one, not the little one. Okay, so there's a quadrilateral. Lots of different names I could call it. I could call it VPQT, QPVT, QTVP. I could keep going. As long as they're in order, it's fine. Parallel lines. When we name parallel lines, we name them in corresponding order. So there's a couple of parallel lines. For this, I would say AB is parallel to CD. Or I could say BA is parallel to DC. So the way the line's running, we keep it in the same order. Equal lines, you'll remember we usually mark with the same symbol. Often it's just a dash or something like that. So in this shape, those dashes are indicating that QR is the same length as PS, because they're both marked with the same symbol. PQ is the same as SR, both marked with the same symbol, in that case, 2 dashes. Now, when we're constructing our proofs, so when we're constructing a proof, anything you put down, any line you write down, has to be one of these things. Some piece of given information in the problem. So if they've given you information in the problem, we can assume it's a fact, and so I can write it down. But I don't assume information is given. This is the classic example. If I'm told 2 sides of a triangle are equal, don't assume it's isosceles. Right? They haven't told you it's isosceles. They've told you 2 of the sides are equal. Now you can use that information to prove it's isosceles. So you could say, well look, AB is equal to AC. That information was given to me. Therefore this triangle is isosceles. And then I can use facts about isosceles triangles. But if they haven't told me the triangle is isosceles, I can't assume it is. I've got to prove that it is. Sometimes in proofs we want to construct new lines, new points to make the solution easier. So you need to write down clearly what your construction is. I'm going to get the line AB and produce it to a third point C. Or I'm going to draw in the diagonals intersecting at X, or something like that. Whoever's reading your proof should be able to reproduce what you're doing. So they need to be able to read it and know exactly, oh, okay, that's what your construction is. They could recreate it. And of course, the main thing we use in geometry is any recognised geometrical theorem or assumption that we know. We can't make them up. If we just make them up, we've got to actually prove what it is we're making up. But there's lots of different theorems that we do know, but it needs to be explicitly stated. Okay? So whether that explicitness is in the reason or whether it's in the algebra on the left-hand side, but it needs to be very clear. And here's the example I've got here about what I mean by explicitly stating. We know the angle sum of a triangle is 180 degrees. So over here, I've explicitly stated that. I've said angle sum of a triangle is equal to 180. I haven't simply just said angle sum of a triangle. Or if I wanted to just write angle sum of a triangle, then over here in my algebra, I would say, hey, these 3 angles add up to 180. So the actual theorem is there, right? Because the theorem says these 3 angles add up to 180. One of my pet hates is when people do things like, they say, oh, well, angle A is equal to 180 minus this, reason angle sum of a triangle. Well, no, that's not what the theorem says. The theorem does not say that an angle in a triangle is 180 minus the other 2 angles. The theorem says these 3 angles add to give 180. So somewhere that needs to be explicitly stated. As I say, whether it's over here in my working or actually writing it in the right-hand side that the angle sum is 180, it needs to be there. Right? The reasoning you write down should be clear and concise. We get very paranoid about what words to write down. What can I write down? What can't I write down? But it needs to be clear that we know that you know the theorem that you're using, that you do actually know what it is that you're using, and you can tell me the theorem. The last thing, of course, then is any working out that comes from previous lines. So, if one line you've done some working out and you found out that angle A is 20, some more working out, angle B is 30, and then you're saying, well, these 2 angles add up to be 180 because they're co-interior angles, whatever it is. Oh, hang on, that doesn't work, does it? But anyway, you get what I mean. Then I can pull those 2 angles, substitute them in and come up with the working. Let's have a look at some of these angle theorems that we should know. And probably the first one, maybe not the first, but one of the very first that we start with is this one here, where we say that the angles on a straight line add up to 180 degrees, because a straight angle is 180. So if I had this sort of problem, classic problem there, there's x, there's 30, oh, what's x? And they want me to put my reasoning down. The way I would write this problem is I would say x plus 30 is equal to 180. Okay? I wouldn't write x is equal to 180 minus 30. That's my working that'll come in the next line. Right. X plus 30 is 180. The reason, straight angle ABC. I mean, I've added in straight angle ABC is equal to 180 as well, but because over here I've written x plus 30 is 180, I could probably just say straight angle ABC. I don't need to say equals 180 again, but that's what I would write down. And then from there I can do my working out and go, well, x is 150. And do it that way. The answer 150 is obvious. The answer, it's very easy. I don't think there's, I hope, fingers crossed, I don't think there's anyone in here that would have got that wrong, except for silly mistakes, of course. The actual answer 150, I don't really care about. That's not really what I'm interested in. What I'm interested in is, can you express your solution? Can you tell me how you're doing it? Which theorem have you used? That's the important bit of the problem. Okay, there's our classic vertically opposite angles, and of course we know vertically opposite angles are equal. So again, typical sort of problem. Now in this case I can't name the angles because they haven't given me any letters to work with. So I'd go, all right, 3x is 39. The reason vertically opposite angles are equal. Notice I did not write vert op. Okay. Vert is not an abbreviation. Well, it is, but not an accepted one. See, I've used the angle symbol instead of writing the word angles. Well, that is a geometrical abbreviation. The equal sign is a geometrical abbreviation instead of saying is equal to. That's okay. Vert means green in French. So are you saying the green, what, those angles are a bit sick, are they? Or, you know, they're green? Yeah. So, no. X is 13. Let's have a look at this one. Angles about a point are equal to 360. Okay. So let's have a look at this problem. If I wanted to solve this one, again, I would write out y plus 15 plus 150 plus 120 is 360. The reason I use is revolution angle. In the same way back here with this 180 problem, I used the fact about a straight angle. Then this one, I'm using revolution angle. It's fine. If you want to put angles about a point, that's fine, because that's true too. What does y turn out to be? Oh, look at that, 75. Okay, let's have a look at our classic parallel line theorems. And there's the situation. You've got a couple of parallel lines, a transversal. I've just labelled all those different angles. We have alternate angles. I don't know how you first were taught about alternate angles, but many, many, many years ago, when I was being shown, and I was told they're the Z angles. Because if you were to just draw in those two angles, you'd get a Z. And that's how you work out which ones are the alternate angles. Okay, it might be a backwards Z in one case, but it is a Z. So you got C equals F. And so if I was just to talk about angle C and angle F, sure enough, there's the Z. And D and E. Okay, it's a backwards Z, but it's a Z. Here's a question for you. Why are they called alternate angles? Say it again. Very good. Did everyone hear that? They're on alternate sides of the transversal. So they alternate, if you like. Yeah. That is exactly right. That is why they call them alternate angles. The actual name has a meaning. Okay. Oh, by the way, when you're writing it down, you don't just simply say they're equal because they're alternate angles, because that's not true. There are two conditions there. They're equal because they're alternate angles and they're on parallel lines. You can have alternate angles. If I've got a line here and a line here, those angles are still alternate angles. They're just not equal because they're not parallel lines. So there are two conditions. So in your reasoning, you need to mention both conditions, alternate angles and parallel lines. Okay, the corresponding ones, I was told they were the F angles. So if you'd form an F, again, could be upside down and backwards and what have you. But so there's A and E would be corresponding, B and F, C and G, and also D and H. Why do we call them corresponding? What does the word corresponding mean in geometry? Do we know that? Same position. Have you ever seen geometry? In triangle ones, we tend to use the phrase matching angles these days rather than corresponding angles. But have you ever heard the term corresponding angles in congruent triangles? Again, they're corresponding because they're in the same position in both of the triangles. Well, that's what we're talking about here. They're on the same position, but on the different parallel lines. So A and E are in the same position, and so on. And so that's why these are called corresponding angles. That leaves us with the third type, co-interior. These ones aren't equal, of course, they're supplementary. I was always told they're the C ones, they make the letter C. Again, you could have a backwards C. So C plus E would be 180, D plus F. Co-interior, why? So that was it? Inside, there's your interior. What about the co? What does co mean? That prefix of co, together. Right? Cooperation, working together. Right? That prefix of co means together. So co-interior means these angles are together on the inside of the parallel lines. So they're on the same side of the transversal, as opposed to the alternate ones which are on opposite sides, together on the inside. Hence the name. See, the names, we don't just make these names up. They do have meaning. Like, all right, let's do an example. We need to find x, we need to find y. I think I'd probably find x first of all. It seems to be the easiest of the two. So how do I set my solution out? I'd go, well, look, x plus 65 is 180. I've got the straight angle, and if I can, I always name the angle. So the straight angle I'm talking about is CQD. So CQD is 180. That gives me x is 115. Now to work out y, I'm going to have to do a construction. There are different constructions I could do. I could produce BP down to the parallel line, create a triangle, and use some triangle theorems. That's not how I'm going to do it. I'm going to draw in a third parallel line. So I'm going to construct xy such that it's parallel to CD and it will pass through P. There it is. Okay? So there's my third parallel line. So now I'm going to say, well, look, angle XPQ will equal 65 degrees. They're alternate angles. And XPB plus 120 will be 180. They're co-interior angles. Using that information, I can work out XPB is 60 degrees. But the angle I'm looking for is BPQ. But in fact, BPQ is made up of XPQ and XPB. I call that common angle. Common meaning the same. So I'm talking about the same angle. I'm just describing it in two different ways. Substitute in 65 and 60, and we get y is 125. See, a nicely set out geometrical proof is a lovely thing to look at. Okay, so when we do get around to it, so you don't need to do these now. Wait until after the half yearlies, of course, and we'll work on them then. But that's what we'll work on.